Today's video deals with what's called the ideal gas equation. In all of our previous videos, we've talked about how when the pressure starts at this and then changes to this, or the temperature's this and it changes to this, the ideal gas equation doesn't deal with if the pressure changes, if the temperature changes, if the volume changes. The ideal gas equation, as you can see, here's the equation right here. There is no P1 and V1 or T1 or P2, V2, T2. Okay, this is just a comparison between, as you can see, the pressure of a gas, the volume of the gas, here's the temperature of the gas, and then there's two new ones right here. So the equation obviously goes PV equals nRT. Okay, a couple of things about this equation. This is like the big gas equation. When you ask somebody, hey, what's one of the important equations you need to know with gases? It's the ideal gas equation, PV equals nRT. Okay, now when you use the ideal gas equation, the pressure, remember there's millimeters of mercury, there's torr, and there's atmospheres. Whenever you use the ideal gas equation, the pressure must be in atmospheres. Okay, when you deal with the volume with the ideal gas equation, the volume must be in liters, no milliliters in the ideal gas equation. Okay, and the temperature, just like always, just like with Charles' law, must be in Kelvin. Okay, and then the two new parts here, this letter N, again, I realize the letter may not be the best choice, is the number of moles. Okay, so if you're given the grams of something, you can use the molar mass and you can convert those grams to moles. Why did they choose the letter N? I think they were literally like, look, we use the letter N for so many other things. Let's just use a letter like the letter M. Anyway, the letter N stands for moles. Okay, so you've got pressure, volume, temperature, and moles. And then the last one here is R, and R is what's called the gas constant. So think back to like the speed of light equals wavelength, not over frequency, wavelength times frequency, okay? And the speed of light was a constant, 3.00 times 10 to the 8th. Or even the energy equation, energy of a photon is Planck's constant times the frequency. A lot of times there are constants, okay? And again, just like the speed of light, just like Planck's constant, R is a constant, okay? Which means it doesn't change. So it's a constant that is always equal to, and here it is right here, 0.082 liters atmospheres on the top and Kelvin mole on the bottom. You will see why that is here when we look at some example problems. Okay. So let's back up here for just a minute. Let's talk about the word ideal. Okay, an ideal gas is like, well, Mr. Johnson, in an ideal world, you know, your parents may say, in an ideal world, you would do your homework every night and you would do all your chores. And, you know, ideal kind of means like perfect sometimes. Like if everything were just right, this is what would happen. Okay, and that's the same thing with the ideal gas equation is, well, everything isn't perfect. Okay, but like many situations with science, the math is really, really difficult if we don't make a couple of assumptions about a gas. Okay, for example, let's say we have a container that's 5 liters, okay, and there's nothing in there. There's no gases, no nothing in there at all. Well, and now you're going to put some gas in there, okay? You're going to put some particles of gas into it. Okay, well now theoretically, do you still have 5 liters of empty space? You don't, because the gas particles themselves are going to take up some of those 5 liters. Okay, so to be considered an ideal gas, there's 2 assumptions that we have to make. One of them is that the gas particles don't take up any space. And then I just kind of say like this, even though they actually do. Okay, and we'll see why in just a second. Okay, and now that these particles are in here, you know, like a lot of times when you put a lot more and more of a gas into a container like propane, it'll eventually will turn to a liquid because the gas particles, the closer they are to each other, the more attracted they are to each other. Okay, so one assumption is that the gas particles don't take up any space, again, even though they do. And we also say that the gas particles aren't attracted to each other. Okay, which again, they are, especially depending on how much gas is in there. So an ideal gas and a gas that obeys the ideal gas equation is a gas that doesn't take up any space and is not attracted to the other gases. And the reason why we use that is because to consider a real gas, not an ideal gas, you've got this equation right here, where you've got an A in here, here, and then you've got a B. So the A accounts for the attractions between the molecules. B accounts for the fact that the molecules do take up some of the space, and A and B change from one. I don't think any of you, even look at that. What if I ask you to solve for volume in this equation? Well, you've got a volume on the bottom here that's squared. You've got another volume over here. It's a gigantic mess, okay? So we are never, ever going to use this equation. That is the equation for real gases, but again, it's not something that we use in certainly a general chemistry course, probably not even in a college introductory chemistry course. Okay, but that is the equation that you theoretically would use if you want to try to take into account the fact that the gases do take up some space and they are slightly attracted to each other. So we are not going to use that equation. We're going to use the much, much easier equation, the ideal gas equation. So let's do a few examples together to get ourselves comfortable with this. So carbon dioxide is collected in a 250 milliliter flask. The gas has a pressure of 1.3 atmospheres and a temperature of 31 degrees. How many moles of CO2 are there? So they want to know moles. So the first thing you're always going to do is you're always going to start with PV equals nRT, and then you're going to solve for whatever they're asking you for. So in this case, they want moles, which is this one. So I need to get N by itself. And to do that, and this is what you're going to do every time, everything else that's on the same side with N, we're going to divide. And just like basic algebra here, we're going to say N is equal to PV over RT. Okay? And so now we just literally plug the numbers in, making sure all of our units are correct. So we're going to put the pressure in first. It has to be in atmospheres. It is 1.3 atmospheres. That's our pressure. Okay, the volume, notice they give us the volume. This is very common. They give us the volume in milliliters. Remember that when something is in milliliters, you simply take that decimal point, which is right here, and you move it 3 spaces to the left. So that becomes 0.250 liters. Okay, now on the bottom, we've got R and we've got the temperature. So let's talk about the temperature first. 31 degrees Celsius, I have to convert that to Kelvin. Simply add 273, there's my 304 Kelvin. And then the gas constant, remember, is 0.082 liters atmospheres over Kelvin mole. So notice that R is on the bottom, so the 0.082 liters atmospheres all goes on the bottom, and technically the Kelvin mole goes on the bottom of that. It goes right here. But notice where it actually is. Okay, it's the same thing as this. 8 divided by 2/5. 8 divided by 2/5 is equal to 8 times 5 divided by 2. The answer is 20. Okay, because when something's in the denominator of a denominator, you can move it up top. So notice so all you need to remember is when R is on the bottom, that Kelvin mole part actually goes on top of the fraction. That's just a math, a fraction thing that you can do. And the reason that's important is because notice what they're asking us for. They're asking us for moles. Now watch what happens here. Kelvin and Kelvin cancel. Liters and liters cancel. Atmospheres and atmospheres cancel. If you have this problem set up correctly, notice the only unit that's left is the unit that they're asking you about. And that's really, really important in science, is that problem is set up correctly because all the other units cancel except for the units they're asking you for. Okay, so then I just go to my calculator, and I would recommend that you try this. I would take 1.3, divide by 0.250, divide by 0.082, and then divide by 304. And you should get the same answer that I got here. Okay, example number 2. Tennis balls contain nitrogen gas to maintain their pressure. If a tennis ball has a volume of 144 milliliters and contains 0.33 grams of nitrogen gas, what is the pressure? So again, start with PV equals nRT right away. And they're asking you for what is the pressure. So to get P by itself, I've got to divide by V. So P equals nRT over V. So the number of moles they don't give me, but they give me the grams of nitrogen. So watch how I do this. I'm not even gonna write the answer. I'm just gonna take 0.33 because I've done this enough now that I know that I need to divide by the molar mass of N2. So the molar mass of N2 is 28. And again, now I've converted that to what? I've converted that to moles. Okay, and then I take 0.082 liters atmospheres, watch how I do this, over Kelvin mole. So when R is on the top, the Kelvin mole goes on the bottom. When R is on the bottom, the Kelvin mole goes on the top. Okay, and then the temperature is 24 degrees. 24 plus 273 is 297 Kelvin. And then the volume is our 144 milliliters, which again, 0.144 liters. Move that decimal point real quickly over to the left. So in the calculator, I'm going to go 0.33 divided by 28 times 0.082 times 297 divided by 0.144. And that gives me a pressure. And notice, like when you squeeze a tennis ball, usually especially when they're new, they're pretty solid, they're pretty hard, okay? Because as you can see, the pressure inside of there is almost double. It is double the normal atmospheric pressure. I get an answer of 2. All right, let's do one more. Example 3, what mass of HCl has a pressure of 874 torr, a temperature of 52.3, and a 2.43 liter container? So they're asking you for the mass of HCl. Okay, but that's not in. I mean, here's our equation, PV equals 102. I don't see mass in there. But they give me the pressure, so let's kind of check things off. They give me the pressure, they give me the temperature, and they give me the volume. And the gas constant, we always know, 0.082. So what's missing here? Oh. And once I have moles, what can I do? Just like how I converted grams to moles here, I can convert moles back to grams in this question. So what am I going to solve for first before I get the mass? The moles. Okay, and like our earlier problem, N equals PV over RT. So the pressure, and again, watch how I do this. I know I need it in atmospheres, and I know to convert torr to atmospheres, I simply divide by 760. Which, by the way, let's come back up here. Remember they were asking us for pressure. Watch again, moles over moles, Kelvin over Kelvin, liters over liters. What's left are our units for atmospheres. So same thing here, our answer should only have units of moles left when we have it set up correctly. So I know I need to convert my torr to atmospheres. So 874, and again, watch how I do this. I just go divide by 760, and I don't even write the answer. I just write 874 divided by 760, and then I write atmospheres, because I know that once I divide those, my answer is going to be in atmospheres. Times the volume, 2.34 liters. That's nice of them. It's already in liters. That's great. R is, again, 0.082 liters atmospheres on the bottom. And remember, there's our Kelvin mole on the top again. And then the temperature, 52.3 plus 273 equals 325.3 Kelvin. And again, if this is right, everything better cancel except for moles. So atmospheres over atmospheres, liters over liters, Kelvin over Kelvin. What's left again? Moles. Okay, so now I go to my calculator. 874 divided by 760. I'm not even going to write down the answer because I don't care what it is. Times 2.34 divided by 0.082 divided by 325.3. Gives me a number of moles of N is equal to 0.10. I'm going to round that to 101 moles of HCl. And now remember, they want that in the mass, so mass is grams. So now I'm going to go 0.101 moles of HCl. The molar mass of HCl is 36.5. I put it on the bottom, and as soon as I did that, I realized I was just about to write grams right there, wasn't I? And then I thought, wait a minute, moles and grams do not cancel. So when you convert from moles to grams, the 1 mole has to go on the bottom, and the 36.5 grams from the periodic table go on the top. Okay, and I get a final answer of 3.68 grams of HCl. Okay, so the ideal gas equation is really, really helpful. It is, again, the big equation when dealing with gases. Yes, Charles' law is cute. The combined gas law, great. But notice the difference in these questions. That these questions are not, the pressure started at this and we changed it to this. These questions are more of a, hey, if the pressure's this, the temperature's this, what's the volume going to be? Kind of those types of questions. Not a, if we change one thing to something else, how does that affect the other stuff?